All right. Hello, everybody. I am Kathy Grise, Senior Program Director in IEEE Future Directions. Welcome to our IEEE Semiconductor Roundtable series, which focuses on different areas of semiconductors, such as our first webinar on packaging and much more. Our second in the series is on navigating the world of EDA, CAD tools, which focuses on the world of electronic design automation and computer-aided design. EDA CAD are crucial to the semiconductor industry as they support and enable the tools, methodologies, and processes for successful circuit and chip manufacturing. The tools and methodologies provide the framework for design, simulation, test, and validation, all contributing to staying competitive in the semiconductor industry. Our subject matter experts will share their knowledge and expertise with a focus on practical applications. This is an opportunity to learn more about how EDA CAD contributes to the semiconductor industry. We welcome your questions as well as comments and your insights. Please post to the Q&A or the Zoom chat. This webinar will be recorded for on-demand access. And I'd like to acknowledge Bernard Lim and Hazel Stoiber for organizing this panel on navigating the world of EDA CAD tools. This webinar is an offering from the IEEE Global Semiconductors Committee, chaired by Kathy Hayashi. We're showcasing EDA CAD tools. Here's just a very brief introduction of the world of EDA and CAD. As I talked about, EDA and CAD are software used in design, simulation, test, and verification of circuits and systems. We start with a concept. Goes to the wafers, silicon wafers, and then to the finished product. I'd like you to check out our website, semiconductors.ieee.org. Key takeaways from today's webinar. It takes a robust framework of software tools and well-defined methodology for a successful result in a design from concept to production. Costs to manufacture silicon are already extremely expensive, and the value of EDA CAD tools help provide first-time right designs for efficiencies in accuracy, cost, and time. Each of our expert speakers will provide their perspectives, insights on how to navigate this EDA CAD world. Here are our panelists and our organizers. I'd like to invite Jyotika Athavale, Director and Principal Architect at Synopsys. She'll talk about framework for designing a circuit to manufacturing, as well as the overall qualification process. I'll turn it over to you. Thank you.
Thank you very much, Kathy, and welcome everyone. I'm really honored to be part of this webinar, and I'll go ahead and share a few slides describing SLM, and I'll talk about what that is and what I do at Synopsys. So let's see, should be sharing my screen now. All right, so SLM stands for Silicon Lifecycle Management, and it's an end-to-end solution spanning concept all the way from concept, through production and in-field phases of product development, and it focuses on silicon health, so covering dependable technologies such as RAS, reliability, availability, serviceability, as well as functional safety. And so we'll talk about here the need for SLM and what is driving that. So various things as we see in our landscape today, including technology scaling and the complexity. As we move to new devices, the transition from FinFET to gate-all-around, the manufacturing variability, introducing more vulnerabilities for extrinsic defects, new trends with respect to chiplets and multi-die solutions, which also require us to consider new failure mechanisms and mitigate those. And then complexity, throughout the stack, including the hardware and software layers, increasing the risk from an aging and degradation standpoint, which is the in-field reliability. Not to also ignore the fact that we are now driving into new mission critical applications which require high levels of safety and integrity, such as automotive. With the ISO 26262 as the governing standard, and its third edition is currently underway. New use cases, moving into robotaxi with the AI training workloads, challenging our systems even more. And the uncertainty that we have with respect to the workload evolution and having the representative test vectors in order to be able to stress our systems before we deploy them in the field. So I could try to see. Okay, here we go. So here's a little bit of an example that I wanted to share, and this is one from a recent publication from one of the key hyperscalers, and that's Meta. And it's on their AI training data set. So this is the Llama 3 model, which is one of their recent training use cases, and they shared the Pareto of the failures that they saw. Using this model across their system. What you're seeing here in the bar graph here is all of the faults that they attributed to the different components across the system, and also, covering both the silent data corruption as well as the detected uncorrectable errors. What they saw is approximately 78% of those interruptions were attributed to hardware issues, with over 50% of them confirmed to, GPU. So the silent data corruption is one of the key reliability challenges facing the industry today and continues to plague us. In addition, another thing that I wanted to highlight was what's driving the need for this kind of monitoring solution for silicon health is the evolution to the new process technology nodes, which is not only stressing our bathtub curve. On the left side, we talked about the extrinsic defects and the manufacturing variability causing higher infant mortality and higher incidence of early life failures, but also the right side of the bathtub curve is now getting stressed because we now see early failures from an intrinsic reliability standpoint, and we are seeing that those defect rates rise, where we see more of that natural wear out happening early on as we continue to stress our systems, given the high performance KPI that we need to meet. And then from a use case standpoint, we don't get any relief there as well. So, typically when we talked about, for example, automotive grade silicon, we were looking at a mission profile of about 8,000 hours over 15 years, which, was well enveloped by our server profile, for example, which requires a more stringent mission profile. So, reuse was easily possible. However, as we are now looking at new use cases, such as robotaxi, for example, for automotive, we are looking at it like an always-on profile and 130,000 hours, through the lifetime of the part, which becomes harder for us to meet. From a technology scaling standpoint, as I mentioned, moving to FinFET, we also are now plagued by the intrinsic reliability considerations. And here we talk about the two key failure mechanisms that continue to to challenge us from the intrinsic reliability standpoint, and that's the gate oxide TDDP, as well as the hot electron, which are the two dominant mechanisms from a transistor reliability standpoint. From an extrinsic reliability standpoint, here you can see that bathtub curve, as I was mentioning, the early life failures increasing as shown by the red line in the bathtub curve. So it's kind of shifting right. And it, interestingly, this is also addressed in some of our new standards activities, including the ones we are driving with IEEE, where we talk about the need for prognostics capabilities because we can have then our eyes on the chip. As you see, this curve continues into the useful life of the part. And so, it becomes critical that we have those detection mechanisms to be able to detect key parameters that are indicative of aging and degradation in the field, such as VMIN. And then we can, take corrective action as needed if we detect an anomaly or find degradation that exceeds our predefined threshold. So what is SLM? SLM, Silicon Lifecycle Management, refers to a solution that spans the product lifecycle all the way from concept through in-field. And it's an end-to-end solution that can monitor the health of the part via these embedded monitors and sensors. It can measure specific parameters. It can transport that data and analyze that data, per certain predefined criteria, and then drive the needed corrective action to recover the system and to extend its useful life. And so here are kind of the use cases. When you talk about SLM, it's really these embedded monitors and sensors, such as ring oscillators, path margin monitors, clock and delay monitors that, measure parameters like frequency, voltage, timing delays, temperature, glitches, things like that. And they then use all those measured information and then process that, filter it, and analyze that information. So here's some of the key ingredients, or what constitutes the SLM product family. There's environmental monitors, like I was mentioning, the process voltage temperature monitors. There's the controllers, there's structural monitors like path margin monitors or XL-BIST, functional monitors like clock and delay monitors and signal integrity monitors, and other solutions here, as you can see, for production analytics, so like for yield and manufacturing, as well as for in-field, improving in-field RAS, as well as functional safety by providing, in-chip data collection and telemetry. And here's kind of that end-to-end solution, which, it spans the hardware elements on the chip, the software, data collection of that information, and then transporting that to the cloud, deriving the analytics, and then the corrective action. Also being able to generate fleet level insights, not just looking at a specific system or component standalone, but looking at the distribution to be able to identify outliers and take corrective action. Also wanted to share some of the key use cases for SLM, including aging and reliability, part performance optimization, and predictive maintenance. So aging reliability is the one I'm going to focus on, as well as the predictive maintenance, which is becoming really key in mission critical applications, to avoid those failures happening early. For example, in an automotive vehicle, you don't want to have a catastrophic event happening in the field, which can cause loss of human life. So here's some examples. For example, one of the key monitors is the path margin monitor, the PMM, which can monitor the delay of logic elements, in say critical speed paths. You can have thermal sensors to monitor temperature in, for example, your hotspots, and be able to use that to calculate remaining useful life, because most of the reliability failure mechanisms are thermally accelerated. And then voltage monitors can be used to detect, large voltage glitches or any significant voltage droop. Okay, so here's kind of, I just wanted to summarize some of the key, the value proposition from an end OEM standpoint. For example, for automotive, how does silicon lifecycle management or these analytics help achieve, overall quality, reliability, and safety of advanced electronics? For a vehicle buyer, you have enhanced serviceability, feature enhancements, higher levels of automotive safety integrity, trust, low costs with respect to predictive maintenance, as well as high reliability, and then prognosis as well as diagnosis. So say you were to have a failure manifest in the field, then using that data to diagnose the faulty element on the chip and then and then fix it in a subsequent stepping so that it doesn't recur. Here's kind of showing updates going into our governing standards for automotive functional safety and how, employing a prognostic monitoring solution such as SLM would improve your, diagnostic coverage and, overall safety metrics, help boosting your safety and helping you get to a higher safety integrity level. Also summarizing here, the solution having the use cases and benefits across levels. So not just looking at component, but it expands IP, chip, system, and then, the item level as well as the fleet level. So in summary, what I wanted to share is kind of this EDA solution, which is the SLM, which addresses the growing challenge of, the need for improved RAS and resiliency of our hardware components. It addresses, with technology scaling, with increased threat surfaces, multi-die packages, and increased safety critical applications, the need to consider these kind of innovations in our capabilities, to improve our health and operational metrics, and to improve performance, as well as safety performance, as well as resiliency needs. So, one of the key buzzwords in the industry today is data corruption, especially, for hyperscalers as well. That is really plaguing that industry. And then last year, with IEEE, we also introduced some new RAS summits to discuss that problem statement further and brainstorm potential solutions. And the one I described today is one of those ways to combat SDC. So that was my last slide. Thank you so much for listening, and I'm going to hand it back to Kathy at this point. Thanks very much, Kathy.
Jyotika, thank you so much. That was a wonderful presentation here. As you talked about, some of the key takeaways that I got was, the level of uncertainty in today's environment of design. And you've said that failure rates are increasing. So everybody kind of hold your thoughts on that, queue up your questions and comments when we go into our panel discussion. And then everybody, I love, your focus on SLM, the silicon lifecycle management, and in particular, the key application in terms of automotive. Everybody is in a car. And we definitely want safety here and reliability. So thank you so much.
Thank you. Thanks very much.
Next, I'd like to invite Oskar Baumgartner. Oskar is the Chief Operating Officer of Global TCAD Solutions, GTS. Oskar will talk about bridging TCAD and EDA from a design, technology, co-optimization perspective. Oskar, Jyotika talked about the overall silicon lifecycle management. With your extensive experience, what have you learned from TCAD tools and solutions for advancing optimization? I'll turn it over to you, Oskar. Thank you.
Thank you very much for the introduction. This has been great seeing the completely different perspective. And now I want to share how we contribute to questions like reliability and other topics that on the high level of EDA needs to be captured, understood, and further processed. And TCAD is a key contributor in this perspective. So we've seen before the electronic design automation software spanning this whole variety, covering the fabrication from verification, design, up to the system level, and then even afterwards in lifecycle management, as shown by the previous speaker. TCAD itself has been for the longest time a supporting approach to the EDA world by giving insight to the semiconductor device fabrication beforehand using process TCAD, or the device operation of the finished or the designed device using device TCAD. And it helps to gain the understanding of the intrinsic physics of the devices or small circuits. And increasingly, it was used to provide also insight into the future development of the industry of the devices, and used for pathfinding and down selecting the technology choices that would be made by the industry. So combining these two worlds, the EDA and the TCAD world, in recent years, the approach of optimizing the design and technology at the same time has become a prominent feature of the industry, specifically on the foundry level, but not only there. So we have different design options, gate length choices, all the margins, and we have technology variables choices that go down to the single device choice or scaling boosters. And they increasingly interact with each other and have an impact on the thing that's interesting to the designer or the people that are actually want to make a product out of the whole thing, and which are the key metrics for devices like power performance or noise margins and so on, depending on what device we are talking about. And increasingly, TTCO, this is a slide from TSMC 3-4 years ago, has been contributing to driving and continuously giving us scaling options that go beyond the intrinsic device performance. So just scaling down the core transistor is not cutting it anymore. And TTCO has been one of the drivers helping moving forward there. So one of these approaches, and one that we followed and provided and used for several studies, is this TCAD to SPICE approach, where we take the intrinsic device, analyze the performance in detail, and put it into a SPICE circuit to extract the key performance indicators. And it's possible to put this into a kind of push button solution where a lot of the physical details are really captured and then condensed down to the key questions that you might have as a designer. And we've seen a lot of interest by customers, partners, and the scientific academic community in these topics. So we really were able to conduct a wide variety of studies on different devices, different cells, and different aspects that keep designers, foundries, and so on busy. And I want to show you a little bit the key components that are required to actually carry out such a technical study. So we'll start by generating the structure and different out of a layout. And so this is basically the designer input, some sort of layout using GDS2 or ACES format. Or it can be generated on a template-based approach if you want to look at different layout choices and variations in an automated manner. And then you can construct the complete 3D logic cell model out of this layout, either using constructive solid geometry, if you are not aware of the specific process physics, or if you want to do a forward-looking study where you make some assumptions about what the technology should be. Or you can go into a more detailed way using process emulation and actually construct your structure out of that, like shown here on the right-hand side for a CFET, for forksheet device. Another component, once you have the 3D structure, is to really understand the parasitic network that comes out of it, because this really depends on the one hand your design choices, on the other hand your technology choices. So it's a core ingredient and one of the drivers of scaling, actually, to understand really how your RC network looks like. So we need an automated way to efficiently extract this from our device structure, and we do this using perturbative methods, and we combine an automated topological analysis of the 3D structure. So it's purely rule-based to actually generate the nodes where we measure our RCs in the 3D structure and then obtain a SPICE net list that we can then later use for our analysis. So this is the one part that's very important. And of course, the other part in the mix is the device itself. So you really want to understand and capture the device physics. So here we follow a hierarchical approach where we have detailed knowledge, also predictive knowledge from simulation or measurements or hardware calibrated data, and extracting device parameters, models that are really predictive over the window that we want to look at. Moving forward, we can extract from these device characteristics IVCV, the SPICE model cards, the other component that we need to actually analyze different cells that are out there. And also this is done in a fully automated way. So we have like an optimization recipe like you would do with measurement, and we can extract those things from detailed TCAD simulations in a predictive manner. And following these optimization steps, we end up with a model card, the second component of our analysis of the key performance indicators afterwards. As mentioned before, reliability is also an important question in the industry. So we can also include reliability models to cover aging information into the simulation flow and variability information, basically generating thousands and thousands of individual model cards representing the variability that you would have across the die with your transistors. Putting all those components together, we can run a SPICE simulation with different circuits and then carry out studies like for ring oscillator, power performance studies, and then we can extract the key values that are really relevant for the designers afterwards if you want to go to block level or system level. So switching energies, delays, ramp times, energy delay products, all the things that would end up in a PDK and basically be the core components of a design. Also, you can start looking into different standard cell these optimizations. For example, if you have the question, is a FinFET technology or a nanosheet technology more suitable for what I'm designing for? What are the trade-offs between those technologies? And how can I optimize or change my design or down select my design choices in a specific manner? So we carried out a study we presented a few years ago in IDM, where we did a detailed comparison between FinFET and nanosheet technology, and that was done in a predictive manner in that sense that we were really looking, okay, what would be the design choices that would open up to the industry a few years down the road when nanosheet technology actually becomes available. Another study we did together with one of our partners, a startup called Cyclarity, that looks into automated design generation and analysis. So they're able to generate and look into a variety of designs, and we carried out a study where we looked at what's the effect of edge placement errors on the design performance, and how would that affect your cell in the end, and what would be the margins that you can look at. So you end up with really moving the detailed knowledge that you have from your 3D TCAD model and doing the variations on the layouts in an automated manner, generating quite a lot of data, but it also gives you insights. It gives you insights where you can see, okay, which of the parameters of the margins, which of the design choices leads to what kind of impacts down the road on your actual performance, like here seen for this ring oscillator study. Another thing, and I think that's very important to tie into the larger EDA world, is it also allows you to generate virtual PDKs beforehand, or pre-silicon PDKs. So you have your basic standard cells that you are aware of that will be out there. You know roughly what the technology roadmap is going to look like. And you want to cut down on the time, on the design times, or gain knowledge beforehand, before the technology actually becomes available to you as a designer. So you need a PDK that is usable for you to do these choices. And this can be generated using this TTCO approach. So we have our pre-selected technology parameters, or our technology assumptions, we have our design assumptions, we can run the machinery and basically generate a library file that you can then later use for your studies on a block level or even a system level, and give you some design advantage and maybe some time back, because the turnaround times are really a big challenge for the whole industry. And to conclude this presentation, so using TCAD and enabling this co-optimization flow between design and technology, we are really able to explore and carry out pathfinding studies that go beyond what's out there in an efficient manner. Okay, we need compute resources, but you don't need to sit there and survey your studies the whole time. And you can really start asking the questions that you're interested in. It allows you to really analyze and understand what the interactions are between making this design and technology choices, and also looking at the previous speaker, what will be the outcome with regard to reliability, doing a study on an optimization on a certain design, and then you want to know, okay, what happens 10 years afterwards? Will my car still work? And ideally, you can narrow this window down a little bit. Also looking at the wider configuration space, you're not allowed to run thousands of wafers necessarily for finishing your design and optimizing it. So some way to do this beforehand and target specific requirements that you might have in your application or in your product from a point of view where the technology is really represented correctly is very important. And of course, we hope to propagate all these insights across the whole EDA tool chain and really help everyone along in this environment to gain new insights and advance their products, their solutions, and their designs. Yeah, and with this, I'd like to give back to Kathy, and thank you for the chance to presenting this.
Oskar, great presentation, a lot of detailed information that you shared. I always try to put together like a word chart, and what I picked up from what you shared was really first and foremost, like scalability, right? Scaling challenges. I heard you talk about reliability, variability, extractions, simulations, all leading to hopefully a successful process design kit, library of elements and things like that, trade-offs, and also most importantly, to help enable a company, for example, on their design choices and ultimately performance. And then the last takeaway I got from you was longevity. And it kind of tied me back to what Jyotika said in terms of the SLM, because like an automotive, a car, some people may want the car to last forever. And so really, when you talk about performance and longevity, that is such a key factor. So thank you so much, Oskar.
Thank you.
Next, I'd like to invite Maxim Ershov. Maxim is the consultant at Maverick. He'll provide insights on how one can start and an EDA startup. So, Maxim, we have heard all the different perspectives, frameworks, design flows, implications, failure rates, reliability, the challenges with EDA and CAD from Jyotika and Oskar. And we'll, take a pivot and hear from you, perspectives on how you have actually, as an entrepreneur as well, scientist and engineer, on how do we start a new community like that, a company, and share your insights. I'll turn it over to you. Thank you.
Okay, thank you, Kathy. Let me make sure you can see my screen. Can you see my screen?
Perfect.
Kathy?
Perfect. Please begin.
Can you hear me?
Yes, we can hear you. Go into
And can you see my screen?
Presentation mode. Yes, we can.
Okay, excellent.
Thank you.
The topic I'm going to talk about is about EDA startups and specifically how to start and build a company as a co-founder. Well, just a couple of words about my background to explain where I'm coming from and why I think I'm qualified to talk about these topics is I spent last 25 years of my professional life working in EDA. I worked at EDA and semiconductor industry. I worked at 6 startups and 2 big companies. Out of the 6 startups, 2 of them were EDA, 9 years at Silicon Frontline Technology, and then Diacopter, where I was co-founder, CTO, and CEO. And both startups were successfully acquired by Synopsys and Ansys, respectively. So one important thing about EDA startups and startups in general, how to make a successful startup. So there is really one secret, okay, is how to make a product that customers will love and will want to buy and use. And everything you do in your startup will be focused on this single purpose. So doing a startup involves risks and rewards. First of all, it's a very rewarding experience, emotionally, professionally, and also sometimes financially. Doing a startup is a very risky endeavor. As we know, 90 to 95% of all startups fail. However, risks can be significantly reduced with a proper preparation and also by listening for good advice. Doing a startup is a very hard work for many years, almost 24/7. However, I like the saying that if you do what you love and love what you do, then you don't have to work a single day in your life. So this hard work feels like a fun and excitement. Also, doing a startup is quite stressful. You will have to do a lot of uncomfortable things to succeed, to do cold calls, business negotiations, networking, and do many other things. So you should be ready for that. And the big question for potential startup founders is, should I quit my job and do a startup, or should I keep my job? Okay, so it's a not easy question. So EDA startups is first of all, it's a startup, and like all startups, the key to success is to follow certain principles, rules, laws, I would say, irrespective of the area of the startup. And this wisdom on how to properly do startup is actually available freely on this website by Paul Graham, who was founder of Y Combinator. And if you want to get a single takeaway from this, my presentation is this web link to his articles, and many of his articles are talking about how to do a startup, when to start it, how to get a good idea, how to build a team, how to get investments, how not to run out of money, how to avoid competition, typical mistakes that kill startups, and many, many others. And my experience of 25 years doing startups is I fully agree with everything that he says. So like his advice became kind of my knowledge, so it's hard to separate which is his thoughts and which is mine. I'm going to talk about specific aspects of EDA startups. So first of all, challenges. EDA industry is a very mature with several big players listed here. And so it's not easy to break into this conservative industry. The ecosystem in a great degree is closed. So there is a lot of proprietary encrypted file formats, methodologies, and it's not easy to operate and navigate this world. Also, the semiconductor industry is formed by these three pillars: EDA companies, foundries, and semiconductor companies. And the gatekeeper for the semiconductor companies for EDA is CAD groups, computer-aided design groups. And it may be counterintuitive, but the practice shows that none of these entities, none of these partners are interested to work with or to help EDA startups. Majority of innovations in EDA used to be coming from startups, and startups are being acquired by big companies, and this is how new tools and new functionalities grow up. But recently, this field has been burned down. Okay? So another problem is that if you talk to your potential users, designers, layout engineers, verification engineers, majority of them may not be that open and interested to talk to you because, again, because of the conservatism and I would say even indifference. Also, the EDA field has changed drastically over the last 20, 30 years. So the practices and the typical approaches, how to build a business, have changed, and old approaches don't work anymore. Another difficulty is that venture capital and angel investors are not that much interested to work with EDA startups because they think it's very low reward investments. So I have this cartoon showing my viewpoint as a startup in EDA, how this triad, foundries, big EDA companies, and semiconductor companies or CAD groups, how they behave towards a startup. So you need to be ready, but these challenges should give you a lot of motivation, because if there is no challenges, the life would be boring. Okay. So on the other hand, building a startup has a lot of attractive aspects. First of all, EDA is very cool, very interesting. It involves physics, mathematics, computer science, design, layout, very interesting areas. And also it combines first principles and scientific rigor and solid foundation with practicality and real-life applications. The foundation of EDA is very solid: physics, math, computer science. So if you build something that relies on these foundations, it will work correctly, reliably, and you and your customers will have high confidence in this, in using the tools. Also, it's good that industry has quite a few people who are innovative, curious, open, adventurous. I'm talking about users in semiconductor industry, and they are open to talk and open to new ideas and to do things efficiently. And these are your friends, and you need to find them. Finding them is not easy. Another attractive aspect of EDA startup is that you can have minimum requirements, minimum investments, and you can do it with a very small team. You can 1, 2, 3 people you can start, and you can do it in your garage or basement or even bedroom. So when not to start EDA startup, again, it's my personal perspective. It's if your primary motivation is to get rich by selling a startup or going IPO, it's not a good idea because the chances are low to succeed. If you are comfortable in a big established company, so if you are okay to deal with some deficiencies listed here, or if you find some good niche and you have some interesting team or good manager, stay with a big company. Or unstable immigration status, or maybe some family obligations may prohibit you to go to this risky path. When to start a startup? So if you are very unhappy about this big company, culture, atmosphere, if you want to make difference, want to do innovative, meaningful work, move fast, to focus on the essential things, also it's good that with a startup, you do things the way you think are the right, and you will talk to the smartest folks in the industry, and it's very nice. Also, if you have a thought that I had in my last startup, so it's risky, it's scary, but if I don't do it, if I don't try it now, I will regret my whole life about this, that I didn't start it. So if you have this thought, it's a good indication that it makes sense to start it. It's very risky to quit your job, but you don't have to quit it in order to do experiments, prototyping, exploration. As Jack Ma, the founder of a big Chinese company, said, you are what you do on evenings and weekends. So it's your free time and you are free to do what you want. Okay? The key challenges in starting an EDA startup is first finding a good idea that solves a real technical challenge and saves time to your potential customers, playing with the prototypes, creating minimum viable product, making a good tool out of that, setting the right price, not too low, not too high, deciding how to do the business negotiations and the sales, getting the first and second customer. These are the biggest problems. After second customer, it's much easier. And then navigating your business and the development strategy. Where to get a good idea? So it's a common advice that, hey, if you work for a big company and you try to do good things, but you think that things are not done the right way and you are not free to change that, hey, go and do it the right way. Sometimes good ideas come from good customers. In general, my experience has shown that in order to get good ideas, you have to be at the front line, sitting in the so-called trenches with engineers, to do the work with them side by side, to feel their pain, to see the problems firsthand, and apply your knowledge and prior experience to see how they can be solved. And I like the saying that goes like, if you want the work to be done well, you need to do it yourself. And as a rule, the customers will not, if you go and ask many customers or potential customers, your friends, like, hey, what's missing? What needs to be done? And they won't tell you what needs to be done. So again, I like the saying by Henry Ford that if you ask your customers what they want, they will tell you, we want faster horse. But when you're creating something new, they don't know that this new can exist, so they won't ask for this. So it's only up to you to decide that. So what makes a good EDA tool that people will love and will want to buy? It goes without saying that the tool should be addressing a critical, a very high pain problem. If the problem is not high pain, people will not pay attention to you. Second criteria is ease of use, clarity, intuitiveness, simplicity. These are the most important aspects of the tool. How easy it is to people to open your tool and start running it. And ideally, the tool should be addressing a large market and be versatile, universal, so that potential number of users can be large in terms of different technology nodes, different circuit types, and whether the tool can be used early on in the design phase, so-called shift-left methodology, or later on for final sign-off verification. Ideally, the tool should not disrupt the EDA flow. It should blend into the flow seamlessly for the user. So the key to that is to use standard non-proprietary open file formats, such as GDS, CCI, DSPF, CDL, UPF, and so on. The output from the tool should be clear, insightful, actionable. Ideally, the tool should have very nice GUI that will drive the user within the constraints, and also should have script or batch mode in order to automate the flow. It should have excellent documentation that is built-in, easily accessible, searchable, and providing cross-links between the tool and examples, tutorials that should also accompany the tool. Of course, it should be stable, robust, easily debuggable, and fixable by the user, and should not require much technical support. Special attention should be paid how you present the tool to the users. So you can do data sheets, presentations, but in my experience, doing a live demo is the most impactful. One picture is worth 1,000 words, and I am saying that one demo is worth 1,000 pictures. So the good demo should convince potential customer to try the tool and to buy and to start using it. And your demo should fit within 5-10 minutes. You should be doing it very quickly. Things nice to have. It's good to have some experience with business development, technical marketing, sales, customer application support. So ideally, you can get it if you have worked in a startup environment. On the other hand, to be at the forefront of the technology to solve this new type of problems, it's good to have exposure to advanced technology or designs or tools or trends. And this can be achieved typically in big advanced companies. It's very important to have a strong team of advisors, supporters, and cheerleaders. And just as one example, one of our technical advisors, he's a professor at the university, he brought us about 30% of our paying customers in our first few years of operation. And also good proper investors who are familiar with your area, who can help with advice and help with the network. Some facts that may not be obvious for newcomers is that you may think if I create a good, excellent tool, hey, it will sell yourself. You just show it or advertise on LinkedIn or somewhere else. It's not like that. Even if your tool is great, it will take a lot of time, energy, innovativeness, how to promote it, how to sell it, how to deliver it to the right people. Another challenge is if you're able to sell 1-2 licenses to a company, how do you grow to dozens or hundreds or thousands of licenses? You need to do evangelizing, promotion. It won't happen by itself, by CAD groups. Yeah. And also typical selling cycle for EDA tools is quite long. It runs from few months to 5-6 years. So you should be ready for that, be prepared for that. And that's all with my slides. Kathy, I'm passing the microphone back to you.
Maxim, thank you so much. I was blown away. You clearly have deep knowledge and experience from as an entrepreneur with startups and particular with EDA and CAD. Very, very insightful and practical advice that you shared with all of us today. So again, thank you.
Thank you.
That concludes the presentations from our panelists. And what I'd like to do then is we have just a little bit of time. And what I'm going to do is pull out one of the questions that Cheaton posed to ask our panelists here. And for those of you that did post questions, we will reply back to you offline from our panelists here. This one is such a relevant topic in today's world, and that is of artificial intelligence. So what I'm going to do then is ask the question, what do you see are the long-term impacts of AI with respect to EDA and CAD? I'll ask Maxim if you'd like to comment on that first.
Oh, sorry, Kathy, I was distracted. Can you repeat it again, please?
Oh, what do you see as long-term impacts of AI as it pertains to EDA, CAD, as well as how does that perhaps enable or maybe handicap startups for the use of AI?
A few days ago, I attended a conference organized by Mentor Graphics or Siemens user to user, and there was a panel on AI for chip design. And I actually really like the attitude of the participants where they said that, hey, wherever AI can help, we should be using it, but we should not think that AI will replace people. Actually, they were saying that designers who use AI will replace designers who don't use AI. It's not like AI will replace designers. So there is a lot of areas where AI can be applied, but my personal opinion is that if the tools are developed with a lot of thought and care, very often it may be more efficient than AI. For example, tool generates a big log file with a lot of mess there. You have to go through these text files and, hey, let's use AI to do that. Hey, you, as a tool developer, you best know what are the important messages, how to sort them out, how to bring to users' attention. So I would say it's a combination of AI with more care from the developers.
All right, thank you. Oskar?
Yeah, I have to agree with that very much. I think where AI definitely will very soon, and partially already does contribute, is help accelerating bits and pieces of the tool chain, especially with regards to optimization. So we've seen on and on again that parts of the designs were in an automated way improved and optimized using different AI models. I also see that as part as using surrogate models to accelerate parts of the flows, reducing simulation time and maybe making use of already generated data, giving quicker access for understanding. So it will be very focused, at least on the TCAD level, on individual questions, individual problems. And I don't think it replaces the need for engineers. It's just another thing that engineers need to understand and be able to do to be more efficient.
Excellent. I'm glad that humans will still be around then and that are needed. I think maybe we have time for one more question, and this one's from Bruce Heck. He's asking about extendability in terms of CAD for multiple domains. The example is the extendability from not just like circuit chip level, but into boards and other applications. Oskar, you want to take that one on first?
I actually think this would be perfectly answered by someone from Synopsys. I think the recent acquisition from or the ongoing acquisition of Ansys shows how much this combination is going on, and of course TCAD is part of it. It's natural that with the challenges, multi-domain simulations and all these things are becoming more and more relevant.
Okay. And Maxim, you want to give it a try, or?
I'll pass on that one. I was typing answers in the chat window to leave. Yeah.
Oh, okay. Sounds fair. We are actually at the top of our hour, and boy, it went fast. I want to thank our panelists today, Jyotika, Oskar, and Maxim, our organizers, Bernard, Hazel, and Kathy Hayashi. We will offer today's webinar for on-demand recording, and we will address all your questions and comments offline. We thank all of you for attending today's session, and please stay tuned for future ones. That concludes our webinar. Thank you all.